Hello everyone and welcome to Medford Anywhere Learning TV. We're glad you're tuned in. We want to give a shout out to our friends at Southern Oregon PBS, KTVL, KDRV, and the Dove Network. Thank you for hosting us on your station. In the Medford School District, we have one shared vision, and that we believe that all are learning, and learning is for all. And what better place to do that than right here on Medford Anywhere Learning TV.
Hi, I'm Erik Horton. I'm a sixth grade teacher at Abraham Lincoln, and this is a lesson on exploring ratios and the real world. Ratios, I'm talking about math. Math, right? That word that as soon as I say it, some of you go straight to fear. You're like, math? Math? We're going to do math? I don't like math. Math makes me nervous. Maybe you're getting a math test and you're looking at it and you're like, math, I can't take it. Why do we do this? Why do we freak out so much about math? It's just a four-letter word. It's just a subject in school. Speaking of which, why do we have this subject every year? You take it in elementary school, in middle school, and high school. Every day you have math homework, you have math problems, you have math tests. And what if you ask your math teacher the question, because I'm sure a lot of you have done this, hey, Mr. Horton, when am I going to use this math in the real world? And your teacher probably gave you a look like this, and then panicked and then went to the first thing they could think of, and it probably sounded something a lot like, you need to know this math to do math next year. Well, that doesn't mean much to you guys as kids, right? Wait, so I have to learn this math so I can do more math, and I keep doing more and more math? I don't see my parents doing this math. I don't see this math all the time. What is the point of this? Well, there are some things that math really can help you do. And while you might not grow up and have a job where you use everything that you've learned or tried in math, math can open some doorways for you. And even if you don't use math or don't think you use math as much as every day in the future, it can still really benefit you. There's three ways that starting at a very young age, practicing math can improve your life. One of those is math helps you grow your brain. It helps you think in different ways. It challenges your brain to make new connections. So I can use these new connections then to explore the world. So I've got to grow my brain, and one way I can do it is math. Another thing that math does that helps me out in life is it makes me a problem solver. So when I get something difficult that I have to deal with in my life, whether it's something like how much dirt do I buy for my garden bed, or how much do I spend on entertainment to make my budget work, or something like how do I spend time with all of my friends but also get my job done. These problems that arise in our life, a lot of times we fail to solve them because we get stuck in this position where if it's difficult, we quit. But by looking at math as a way to learn to solve problems, we can use that in the future for whatever problems come into our lives. And thirdly, if I can use math to grow my brain and solve problems, then I can start to understand the world around me in a different way. Maybe it's seeing shapes all around you, or understanding how things are connected together, or why something happened, or economics, or personal finance, or the list goes on and on. Maybe it's something as simple as, how many views per day am I getting? Is it enough for me to become a famous YouTuber? I don't know what's important to you, but math can help open those doors. So if math can do all of these great things, why do so many of us not like math? Well, it probably breaks down to the way you're learning math in class or the way you are approaching math. And I'm going to use an example or a metaphor. Think about art class. If the way art class or all art went was I showed you a picture and I said, guys, this is the picture we're going to make. We're all going to make this exact same picture. Now follow my steps perfectly and do exactly what I would do. What we would end up with in a classroom is an entire class of the exact same picture, except none of them would look as good as the picture we started with probably. So if all you're doing is following step-by-step examples and trying to reproduce something that somebody else has worked on for a long time, then we're going to end up feeling like our math wasn't good enough or our art in this case wasn't good enough. But if I give you the supplies and I say, play around with this, see what you can make, we would get a whole classroom full of different ideas. And these different ideas or representations through art would be amazing to look at. Some of them might even turn out better than the example in the step-by-step drawing. So how does this work with math? Because you're telling me if we did math like this, then kids are going to come up with the wrong idea. Yeah. Sometimes we come up with the wrong idea. Think about your life. We make mistakes. Your parents have made mistakes. Your teachers have made mistakes. And you have made mistakes. But learning from those mistakes is how you grew. That's how you became better at something, is by making those mistakes. And so in math, we need to be allowed to make mistakes to grow and to think differently. So what's a good environment for this? And that comes to another word that I want to start talking about today. And that word is play. How do we play with math? How do we play with math to grow our brains? How do we play with math to solve problems? And how do we play with math to understand this world that is all around us? Well, so today we're going to look at ratios, and we're going to figure out how this word ratio works with the things that I'm talking about. How can I play with ratios to solve some problems that exist in the real world and help me understand what I'm doing? So we're going to start at the very, very, very beginning. And I've got right here, I'm going to write this word ratio. And what a ratio is this is an understanding or a relationship between a group of numbers. And so this ratio we're going to do, we're going to pretend we have 30 kids in our classroom, okay? So there are 30 kids. And we are going to say in this, 12 of those kids are girls. And I know in a real world, we're thinking half are boys and half are girls, but I'll tell you that's not always true. I'll tell you, in my class this year, I think I had 12 girls out of 30 by the end of the year. We started with like 10. So that's a realistic number. I got 12 girls and 30 kids total. So I have a ratio of 12 girls to 30 total kids. How can I represent this? Well, you've had some practice with fractions, hopefully. And so you're thinking in a fraction, I've got this fraction line, and I'm going to put a number here, and I'm going to put a number here to represent my fraction. And in those fractions, the bottom number is my total. The bottom number is my whole. And so my whole here is 30. I have 30 kids total. And then the part to this is the 12, the girls. I have 12 here. So now I've created a fraction that represents my ratio. My ratio is 12 out of 30. Just like this. Just like this symbol I drew here. You know what's really interesting about this symbol? That makes fractions kind of more easier to swallow or understand. You've probably seen this symbol before because it's on your calculator. It's the symbol for division. A fraction is a division problem. Really, this is 12 divided by 30. And this gives me another way to look at that ratio. So I'm kind of playing with this a little, but I'm still in a very number-based school fraction mode, and I haven't really started to use any toys yet. I don't know about you, but do you like to use toys when you play? Because my kids like to use toys when they play. They like to use toys and imagine things and move them around and see what they do. So how do I include a toy into this ratio? Well, a lot of times in math, your toys are kind of like tools. And as you grow up, a lot of your toys and tools are still the same thing. So I'm going to show you this tool that you can use. I've got 12 over 30, and I'm going to create my first tool, and this is called a table. And it's important that in my table that I label what I'm doing. So here at this side, I'm going to write girls. And then over this side, I'm going to write what the whole is. What I want you to do is start thinking what's going to go there. That's right, my total goes there. So now I have girls on one side and total on the other side. I'm going to fill in this table. I know there's 12 girls. What do I write over here on the total side? Well, I look at my denominator for my ratio here, and I've got 30. Well, okay, so now we're just organizing our toys. This is kind of like when you're going to play with your Matchbox cars and you and your friend, you just kind of start picking cars. We're just setting up. We haven't even started to play yet. So I'm going to ask you another question to go with this. I've got 12 girls out of 30 total. What if I had 60 total? What if my ratio was the same, but I changed it to 60? How many girls would I have in that class? Well, you might earn that in that group of classes. You might think 30, okay, plus 30 gets me to 60. So I should do something on this side. But I have to keep my ratio locked in. I cannot change the fraction relationship. So what does go here? Well, let's go back to our fraction here. I've got 12 over 30, and we've had some experience with equivalent fractions. If I have 12 over 30 and I want to change it into 60, then what I really did to make this equivalent is I doubled or I multiplied 30 by 2. And because the ratio has to stay locked in, I've got to do that same thing to the other side. So I multiply 12 by 2, and that gives me 24 over 60. So what goes in this little space here? My ratio stays locked in. I can now continue this pattern and say, well, this is multiplied by 2, and this is multiplied by 2. If I'm using multiplication here to play with my ratio, I can find any of these numbers and keep my ratio locked in. What if instead of 60 kids in the total and the ratio stays the same, what if I'm talking about a really big school? And I'm talking about the entire school, and I come up with a number like 330 total kids in the school, but it still has a ratio of 12 to 30. Well, what did I do to 30 to get 330? Well, I'm multiplying here. And what am I multiplying by? 30 times 11 will give me 330. So I have to do the same thing to both sides. If I multiply by 11 here, if I play with the numbers and I get 12 times 11, I've got 132. My ratio stays the same. I wonder if this ratio has to stay this large. What if I want to reduce the ratio even smaller? So here I've got 12 and 30. Can this go the other way? Now, I have to start thinking about what are some factors. I'm playing with 12 and 30. What are some numbers that go into both of those? Well, they're both even, so 2 goes into both. And 3 goes into 30. Does 3 go into 12? Yeah, 4 times. As I continue to play, I can figure out that I can get to 5 out of 30 by dividing by 6 here. Can I divide 12 by 6 evenly? I sure can. When I divide 12 by 6, I end up getting 2. I have reduced my ratio down to 2/5, but the ratio is still locked in at the same relationship between the part and the whole. So this is how I begin with ratios. All right, so we've looked at some ratios. But how often are we talking about how many kids in my class are girls versus how many total kids there are? You're like, I'm not going to be a teacher, Mr. Horton. How am I going to use ratios in another way? Well, I bet you like to shop. And when you shop, you're talking about ratios all the time, especially if you're getting more than one product for a certain price. So let's say I go to the store and I'm going to make a purchase. And in this purchase, they show 3, we'll call them sports drinks. And these 3 sports drinks are going to cost $5. I get 3 sports drinks for $5. This is a ratio. For every 3 I buy, it costs me $5. If I want to buy 6, it costs me 10. If I want to buy 9, it costs me 15. I'm multiplying by the same thing because I'm keeping the ratio locked in. But how much is this costing me for one? And if I set this up in a table and I've got 3 on one side and 5 on the other. And I want to know here, this is my drinks and this is my money. And I want to know what 1 is. I can divide by 3 here, but when I divide by 3 here, I get 5/3. Well, I don't know about you, but I don't know how much $5/3 is off the top of my head. So here I'm going to have to use some division. And this is, just like I showed you, fractions are division. So I have 5 divided by 3. You know, and I can even break that into a whole number and say 5/3 equals 1 2/3. Well, this is easier to understand. $1 and 2/3 of a dollar. And if I used my calculator or I did the math, I would come out to $1.66. Or usually the store is going to round it to $1.67. This is $1.67 per 1 can. 5/3. So now I've played around with these math numbers. I've played around with the ratios of how many kids are in class. I've played around with how to shop and use unit rates to figure out how much I'm actually spending and if this is a good deal or not, because I could compare this to an individual price and see what I'm saving. That's real world math. That's real world ratios. Almost everybody at some point in their life gets to go to a restaurant. All right, so let's say we go to a restaurant. We're celebrating our great grandma's birthday, and everybody goes out. And at this restaurant, we order a bunch of food, and our final ticket comes, and we spent $60 at a restaurant. And I want to talk about how to use our math and how to play with this math to come up with solutions that aren't always the exact step-by-step solution. I've got $60 at this restaurant and I'm going to leave a tip. And let's say that the standard tip is a 15% tip. So now I've moved from ratios to rates to now we're talking about percents. And guys, percents are just ratios. What they are is they are a ratio or a relationship between some number and 100. In fact, the word percent here has cent in it, which means 100, and per, which tells me I'm probably going to divide. I'm going to divide something by 100. All right, and so my percent is 15. Now, how can I play with this? Well, I could show you a step-by-step way to set it up with just the numbers, where maybe we take 15 over 100 and we multiply it by 60, and then we reduce and we divide. But that's not that fun for some of us, and it's certainly not using any tools or toys. So one of the toys we can use here in math to help us kind of understand this and get to an answer is to use a percent bar or a double number line. And so I'm going to draw this really cool rectangle, and I'll tell you, this is one of my favorite toys to play with in math. And I didn't draw that very well. I'm going to try to make it a little better. But this is a percent bar, and in this bar, we know that all the way over here, I got 0%, and over here I've seen 100%. You've probably seen this when you're installing something on your computer and you're like, okay, it's loading, it's at 13%, it's at 40%, and you're watching it get to 100. Well, at 100% here, we're gonna fill in some of our ratio relationship. I've got 0%, 100%. I know that right here, over 100%, I have $60. 100% of my bill was $60. What do I want to know? What am I playing with? Well, my goal here is to figure out what 15% is. And these numbers on this number line are locked in. I can't change it. $60 is always 100%. So let's play with the numbers. Let's have some fun. What if I wanted to know what 50% was? Well, that's half of 100. So what's half of 60? $30. Okay, that's getting me somewhere. What about, I could find 10%. 10% is 100 divided by 10. So I'd be dividing by 10 here. I could do that to 60 and find $6 here. I could find half of 10% and get 5% and do half of 6 and find $3. I can add 10% and 5% to get 15. I can add 6 and 9, and that will tell me my answer is 9. But I could also go all the way to 1% and find out 1% is 60 cents, and I can multiply back. I could find all kinds of different ways playing with this tool to understand different percents. I can take my 15% and my 100%, and I could add them together, extend my line, and get 115%. I could take my $9 then and add it to 60, and I would get $69. I know how much I have to spend with tip by using this tool. And it's pretty cool, and it's pretty fun. It's not bad at all. So we kind of worked through what most sixth grade rates, ratios, and percents are, how you work together with them, how you keep it locked in, and how you use it in the real world. But how does this translate as I move forward? Because Mr. Horton, you said that I need to know this math so I can know it for next year. And not every type of math uses just percent bars or tables or works with that. Sometimes I need to understand an equation. How does an equation work together to understand a ratio? So I've got an example from you from some 7th grade math stuff. If I wanted to tackle the idea of figuring out this mythical, long lost thing called pi. Now, we've heard of it, and a lot of us have done math problems, and the teacher or an adult or the assignment or even Khan Academy says, hey, you got to just plug in pi, multiply it by pi. And then people are like, well, what is pi? Because it doesn't smell like apple pie in here. Well, and then they tell you, use 3.14. What does that mean? Use 3.14. And who figured this out? I'm going to let you know a little secret. It's actually a ratio. You could take a circle. So here I've got a circle, and I'm going to take some measurements, and that's actually probably the best circle I've ever made. Here's a circle, and we're going to label some things. We've got a radius, and I'm going to give that radius a number of 3.5, just for fun. So I've got a radius of 3.5, and the measurement all the way around this circle is going to be 22. And this is called my circumference. My handwriting is terrible there, sorry. And this is my radius. Now there's an equation that tells me that my circumference equals 2 times r times pi. Well, let's plug in some numbers and figure this out. If I plug in my number for my radius here, 3.5, I have 2 times 3.5, and that becomes 7. Now I have 7 times pi equals c. Now if I follow my algebra steps and I divide both sides by 7, I know that my circumference is 22. If I divide both sides by 7, these 7s cross out because anything times 7 divided by 7 gets me back to the beginning. I now have just pi on this side, and I have 22 over 7 on this side. Now, I'm going to spare you the little division here, but if I were to divide 22 over 7, I would actually get an answer of 3.14 and some loose change. So the ratio of my circumference to my radius always comes out as pi as long as I'm using a perfect circle, in which case we're pretending that what I drew here was a perfect circle. So you're saying ratios and circles, that's all good, Mr. Horton, but does it stop there? No, wait, there's more. Ratios actually can show up in some pretty cool other shapes called triangles. And if I draw this right triangle like this, and I make like a little marker here, I've got A and B and C. And I'm going to give some values to A, B, and C. And I'm going to say, let's call A 3. And let's say B equals 4. What does C equal? And can it equal anything? Well, the answer is that it can't just equal anything. It has to equal a certain thing based off what A and B are. And this guy Pythagoras, he developed the Pythagorean theorem, which tells us that A squared plus B squared equals C squared. But how do I know that's true? I can play with math to figure this out. What if I took this right here and I made a square out of it? Now I've got a 3 by 3 square. The value of this 3 by 3 square is 9. And I'm going to erase this and move it. And I'm going to make a square here out of this. Now I've made two different squares here, and I know the drawing's not perfect, but like I said, this isn't step-by-step art. I'm having fun. I'm playing. When I make a 4 by 4 square, I have 16 squares inside of it. There's actually a connection here, a ratio between these, where 9 and 16, if I took all of these blocks and I jarbled them up and I made a square here off this angle, I would have 16 and 9, I would have 25 squares to work with. If I made a square out of 25 squares, that square would be 5 by 5. That square would be 5, 5, 5, which would mean the length of C is 5. So this proves that my A squared plus B squared equals C squared. So how is this a ratio, Mr. Horton? Well, it's a ratio because if I were to divide these, both sides by A squared and B squared, both sides, then I find that there's a ratio between the C squared and the A squared and B squared. A lot of times, if I were to put numbers in here for A and B, I would end up with a crazy number for C, something like 4.17832, and without a calculator or a lot of time on my hands, it's going to be difficult to come up with that. So this 3, 4, 5 makes a very cool whole number ratio for this triangle. Are there other ones? There are. Some of the other ones happen to come from using my understanding of ratios. Check this out. What if I went all the way back to the beginning and I have my triangle, and instead of 3, 4, 5, I say I want this to be 6 if I multiply it by 2. Well, since it's a ratio, I need to multiply this by 2 and get 8. Now I have 6, 8, and what is this going to become? Well, 6 squared is 36. 8 squared is 34 or 64. Added together, they're 100. What times what is 100? 10. 5 times 2. I multiplied all of these by 2. If I took these same things, if I took 3, 4, and 5, if I multiplied 3 by 3 and 4 by 3, guess what? The hypotenuse is going to be 5 by 3. All of these ratios work in this way. As long as you keep your ratio locked in, you're going to be just fine. Now, I challenge you, play with some math this week. Play with some math this summer. Get comfortable with it. Don't be afraid. It's not just for next year's math. It's going to help you grow your brain. It's going to help you solve problems in the future. And it's going to help you understand the world around you. Whether it's shopping, circles, triangles, construction, any of that stuff. How many tomato plants to plant in my garden, how much space I have. Think about the ratios, think about the math, and have some fun. Don't be afraid. Thanks, guys. Thank you for watching Medford Anywhere Learning TV.
Thanks for tuning in to Medford Anywhere Learning TV. Medford School District is a place where all are learning, and learning is for all.